couple of minutes, I'm going to give you an overview of neuromorphic computing, which includes SpiNNaker and also the BrainScaleS system at Heidelberg. Now, why neuromorphic computing in the Human Brain Project? Well, from the outset, the Human Brain Project had three primary objectives that motivated the funding of the project in the first place. The first of these was to advance our understanding of the brain, which is still very little understood at the level of information processing. The second was to understand brain diseases and contribute to improving medical care in society. And the third motivation was to develop future computing. And this is brain-inspired computing technologies of various forms. And the major brain-inspired computing technology that is developed or advanced within the HBP comes under the heading of neuromorphic computing. And in the HBP, there's activity on building silicon, building machines, algorithms and architectures, underpinning theories and applications of this neuromorphic technology. Neuromorphic computing can be traced back to the work of Carver Mead in the 1980s, and of course we heard about this in our opening keynote this morning from Giacomo Indiveri. The fundamental observation Mead made was that the equations that describe the flow of ions in ion channels in neurons and the equations that describe the flow of carriers in subthreshold analog transistors are basically the same, and therefore you can build electronic circuits which are physical analogs to the biological circuits. And in the 80s, Mead led the development of neuromorphic sensors such as touch and hearing and vision, and the field has developed from then and diversified in a number of directions. So within the Human Brain Project, there are two principal platforms, the SpiNNaker platform and the BrainScaleS platform. Both of these predate the HBP and were the original technologies were developed in earlier projects. But within the HBP, they've been brought together and are offered as open platforms. They're scaled up, and the HBP offers software support for their use. Also within the HBP, there's been work towards developing second generation versions of both of these machines, and these are now coming to fruition. The SpiNNaker system uses a many-core computing approach and is based on simulation, so that neurons are modeled in software, and so are synapses and learning algorithms. Whereas in BrainScaleS, this is closer to Mead's original concept of using electronic circuits that emulate the biological systems. Both of these machines are large-scale machines which have been built by their respective teams from the transistor upwards. And of course, in the wider world, there are many more neuromorphic machines around, and you can sort of put these on a scale of increasing biological realism from left to right and increasing sort of flexibility and ease of use from right to left. So SpiNNaker is really at the very flexible end where software is used for all the key functions. BrainScaleS has many functions cast in hardware, and in the middle there are some well-known industrial prototypes such as the IBM True North chip and the Intel Loihi chip, which are somewhere in the middle between these two systems. They both implement the algorithms in digital hardware, so they're not analog circuits, they're digital, and they're highly parameterized, but they're not as flexible as the software that you find on SpiNNaker. So through the rest of this session, we're going to tell you how you access these machines, what they can do, and we'll go into a bit more detail on each of these